Hi, everybody. So can you hear me? Fine. Great. Any questions, problems, difficulties you want to talk about? Okay, let me share a screen and share content screen. Okay. All right, so let me see. So we started to talk about Brenne's polar factorization theorem last class, and I was talking about the situation where the hypotheses become symmetrical in X and Y, and so you can map forwards or backwards, and the backwards map will be the inverse almost everywhere of the forward map, and vice versa. And so we come to Brenne's polar factorization, which said if mu is absolutely continuous on Rn, and F, you have a map F from Rn to itself, such that F pushes forward mu to a measure which is also absolutely continuous with respect to Lebesgue measure, then there exists a convex function u, possibly infinite valued, and a mapping S such that two things happen. First of all, F can be written as the composition, and S pushes forward mu to itself. So that was the theorem, and I think I'm due to give a proof of this theorem. Are there any questions about the theorem yet? So maybe before I give the proof, let me try to motivate it with some of its applications. So we also talked about how if mu was a Gaussian, if mu plus was a Gaussian, mu minus was a Gaussian, then the mapping between the two things would be linear. So if mu plus is Gaussian, say the standard normal, and F is linear, then we saw last class that mu minus is also Gaussian, sorry. That's supposed to be defined. F push forward, mu also Gaussian. And so in this particular case, so what does it mean for F to be linear? It means that i.e. F of X is AX for some matrix A. And I guess if I want this not to be a degenerate Gaussian, in other words, if I don't want it to concentrate, to vanish outside some lower dimensional subspace, I want the matrix A to be an SL R SLN, so invertible, in other words. And that's exactly, the invertibility of A is exactly what I need for this image here to be absolutely continuous with respect to Lebesgue. Otherwise the image is going to be concentrated on a lower dimensional subspace. And then in this case, what Brenne's theorem is telling you is that you can write the mapping AX as this funny composition, but it's going to turn out, we'll see in the proof, that the convex function u is going to be quadratic. So the du is going to be linear, and the s is going to be then linear as well. AX is going to be, let's say, P, that's the linear mapping U, and then Rx, where U of X is 1/2 XPX. So in other words, P is positive definite. That's the convexity of U. And R here is going to be an orthogonal matrix. And that's, let's say, let me make this the standard normal Gaussian. And so S will be either a rotation or a reflection, and rotations and reflections preserve the standard normal Gaussian. And so what this, in this particular case where I dealt with the standard normal Gaussian in a linear map, what Brenne's theorem is telling, this of course holds for all X. I mean, so Brenne's theorem tells you that this holds F equal blah, blah, blah. So this, let me change colors. Brenne's theorem tells you this holds mu plus almost everywhere. But in our case, that means all, in this example, that means all X. And therefore, it's telling us I can write an arbitrary invertible matrix as the product of a positive matrix and an orthogonal matrix. So that's one implication of Brenne's theorem. And another implication, so that's, I guess, what is that, the polar factorization of matrices? Right, which is, I guess, why this is called the, I mean, Brenne called this the polar factorization of vector fields, but it should be called the polar factorization of maps. And in this example, it reduces to polar factorization of matrices because it's allowing you to write an arbitrary invertible matrix A as a product of something positive, like a radius times a rotation. And there's another kind of heuristic implication of Brenne's theorem, which is which happens when you take F to be close to the identity map. Does anyone want to take a guess as to what it is? If F is close to the identity map, then when I decompose it as this product, both of the factors, at least heuristically, we expect to be close to the identity map as well. So what do you expect to get out of this F equals gradient of a convex composed with mu plus preserving map? So this was example 1. And this is a bit heuristic and right. If f of x is x plus something, let's say plus t times a vector field v of x, you expect, well, first of all, if t is 0, so t equals 0 implies f is the identity map, and then f equals grad u equals s equals the identity, and u is the convex function 1/2 x squared. So the gradient of that is the identity map. And if t is non-zero, but small, then you might expect that u of x is going to be close to what it was when, in the case of the identity. So 1/2 x squared plus t something, let's call it t5x. And s of x, you expect also to be close to the identity, maybe plus t something again, like tw of x. And so if we plug this expectation into this formula and we read off the terms that are linear in t, so f equals grad U composed with S. So what are we going to get at order T? Well, does anyone want to take a guess? This is kind of the question I was asking a minute ago. Well, so I want to, of course, the gradient of U here is the identity map plus T gradient of phi. And when I compose that with S, I get, I guess I get a d phi, and I get a W, and then I get higher order terms. They would be terms of order T squared if everything was analytic. And of course, F in this example was X plus TV. And so equating things at the coefficient of T tells me that that Brenne's theorem is telling me I can write an arbitrary vector field V as a gradient plus W, where this thing here is supposed to be measure preserving. And so what that means, it's supposed to preserve the measure mu plus, but what that means depends on what mu plus we chose. So for example, if I chose mu, if I fix a domain omega in Rn, and I choose mu plus to be basically Lebesgue measure on omega, properly normalized. So in other words, to be a probability measure, sorry, not on the boundary, on the interior. Then what it means, so if S is measure preserving, of course, the identity is nice and measure preserving. And it means that when I move things around by the vector field W, I'm still preserving Lebesgue measure in this case. And so what does it mean to preserve Lebesgue measure? It means that divergence of W had better be 0. And that's at the leading order term. So there would be corrections, little OT corrections. And if we chose some other measure, then it would be you'd have to modify the divergence operator to adapt it to the geometry of the measure that we'd chosen. And it also means that on my domain omega, sorry, I have in mind omega as a bounded domain compact. It means that W had better be tangent at the boundary in order to preserve Lebesgue measure. So the first line is on all of omega, and you have this kind of normal component of the vector field vanishing on the boundary. And so at this order, what Brenne's theorem tells you is that you can write an arbitrary vector field as a gradient plus something divergence free. Has anyone seen a theorem like that in a different context? So I guess this is sometimes called like the Hodge-Helmholtz decomposition of vector fields. And Hodge-Helmholtz actually tells you that, the Helmholtz, I don't know. Helmholtz tells you that L2 maps from, I guess, omega, L2 vector fields on omega decompose in a canonical way into, so L2 becomes a direct sum for this decomposition. So this is like L2, how do you write it? Gradient plus divergence free. So this would be indeed L2 omega Rn divergence free. plus L2 gradient vector fields. So some of this theorem about the Hodge-Helmholtz decomposition is like a linear theorem that says I can write an arbitrary vector field as a linear sum, and Brenne's polar factorization is a kind of non-linear version of that that says I can write an arbitrary map as a composition of two guys. So that's I think that's kind of cool. And I mean, actually, for a long time, so there's a Helmholtz decomposition that works for forms of higher dimension, like not just vector fields, but 2 forms and 3 forms and things. And for a long time, people wondered if there was some kind of nonlinear analog of Brenne's theorem for forms. And I don't know what the status of that problem is. I know that Gangbo and Decomposition have worked a bit on it, published some results on it with collaborators. So. So somehow this Brenne, this nonlinear decomposition of Brenne's unifies the polar factorization of matrices on the one hand and the Hodge-Helmholtz decomposition of vector fields, at least at a heuristic level, on the other hand. Okay, so now I wanted to try to sketch a proof of Brenne's theorem. And so what's the idea? The idea is to let mu minus be f push forward mu plus, and choose the bilinear surplus function or the bilinear benefit function. And then recall from what we've seen in the last week or so, there exist 2 convex, there exist convex functions u and v such that gradient u pushes forward mu plus to mu minus, and gradient v pushes forward mu minus to mu plus. In fact, v is you can take v to be the Legendre transform of u. And they're inverses to each other almost everywhere. Sorry, this should have been a y. And so the picture is you have mu plus over here, some measure on Rn, and you have mu minus over there. They're both absolutely continuous with respect to Lebesgue. Of course, you have this mapping F that pushes forward mu plus to mu minus, but you also now have another mapping gradient U, which pushes forward mu plus to mu minus, and you have a backwards map gradient V, which is basically the inverse of gradient U, which pushes forward mu minus to mu plus. And so, so what I want to say, because of these inversion relations, I want to say that I can write F in the form, grad U composed with something. And so if I compose it with grad V, then I have so right, so this composition here is like the identity map. And so that's true mu minus almost everywhere. No, mu plus almost everywhere. And so if this is grad U composed with S, where S is dV composed with F. And so the only thing remaining to check is that S is a measure preserving map from U plus to itself. And that follows from the fact S pushes forward mu plus is equal to dv push forward F push forward mu plus, because push forward and composition's factor, push forward is a homomorphism or whatever of composition. And so that's dv push forward mu minus, but we know that dv push forward mu minus is mu plus. Any questions? Okay. Right. So the next topic on my agenda is I don't think Hernieu's listening synchronously, but I wanted to address Hernieu's question, which was, how can you see that that when you do these optimization problems without going to the dual problem, is there some way that I can see that the Kantorovich optimizer connecting mu plus and mu minus is actually concentrating on an n-dimensional subset of a 2 n-dimensional space? And so to answer that, so let me introduce a new condition. So we say, if let's say, let's stick with Rn cross Rn, that's fine. So let's say B is twice continuously differentiable on Rn cross Rn, or on a manifold. Of n-dimensional manifolds. And B is non-degenerate. X naught, Y naught. If and only if. There's a couple of different ways to write this, but one way to write it is the following. The determinant of Bij, or let's say Bi comma J, I don't know. Yeah, that's better. Where by Bi comma J, what I mean is the matrix of mixed partials where I take one derivative with respect to Xi and one derivative with respect to Yj. And there's an equivalent well, there's a more geometrical way of formulating this, but maybe a more topological, but maybe I'll just leave it at this for right now. This way it works perfectly well in Rn. And of course, I mean evaluating this matrix at these partial derivatives at X naught, Y naught. And so the point of this definition is that whenever you have a non-degenerate cost, then locally around X naught, Y naught, the optimal transportation behaves a lot like it does for this cost here, for the canonical bilinear cost. And more or less the proof of this is by Taylor expansion, but let me write a theorem, kind of a nice theorem. So if I fix probability measures mu and nu on manifolds, on n manifolds, m plus and m minus, and B non-degenerate, at X naught, Y naught. And then what's the conclusion? Then there exists R bigger than 0, such that if I could write this in a nicer way, but anyhow, if gamma is B optimal, then the support of gamma intersect intersect a 2n dimensional ball of radius r around x naught, y naught is contained in a Lipschitz submanifold L. And I didn't, let's see, I should, to get the order right, I should say there exists an n-dimensional Lipschitz submanifold L such that sorry, to get the order right, so that when I'm fussing about the order, but so really I should say then there exists an L such that if gammas be optimal, the support of gamma is contained in L. But in any case, that this shows you that at least locally at x naught, y naught, the support of gamma, although it could potentially be 2n dimensional, is actually only n dimensional. It's this sitting on this half dimensional subset. And notice there's no, so what's to notice? So notice no twist assumption. And no need for mu plus and minus to be absolutely continuous. So this is a very general situation. And of course, twist is a global assumption about the behavior of B. Non-degeneracy is a local assumption about its behavior at a particular point. But on the other hand, this non-degeneracy and twist are connected to each other in the sense that one is kind of the linearization of the other. So twist was asking for some map to be globally injective. And when you linearize the inverse function theorem, or the implicit function theorem, I guess the inverse function theorem tells you is a sufficient condition for local injectivity. And that's somehow the relation between twist and so twist asked for every x naught, you have y in m minus goes to derivative with respect to x of b x naught y 1 to 1. If I linearize this, by varying y, I would have that sort of like delta y in the tangent at y naught to m minus mapping to second derivative with one set of derivatives with respect to x, the other set with respect to y at x naught, y naught, goes to this matrix acting on delta y. And if this, so this is somehow this is an n-dimensional space, and this is taking values in an n-dimensional space after you compose with delta y, and for this linearized map to be 1 to 1, I need exactly the non-degeneracy of this determinant. And if this linearized map is 1 to 1, that's a local condition for the nonlinear mapping to be 1 to 1 by the inverse function theorem. So in some sense, non-degeneracy is a kind of strong, it's a locally stronger but globally weaker version of twist, because it says not only is the mapping locally 1 to 1, but when you linearize it, the linearization is also 1 to 1. Strengthens twist locally, weakens weaker globally. And the other thing about non-degeneracy is, remember we define when we said, okay, let this map be 1 to 1, and then define the cost exponential. We define bx xp equals y if and only if p equals dxb xy. So this b exponential was kind of the inverse of this one-to-one map. And non-degeneracy is exactly the implicit function theorem condition that you need for this inverse map to be smooth or to be differentiable or whatever. All right. And so, but let me try to sketch the proof of the theorem. And actually, the proof of the theorem is pretty close to what we've already seen. We already saw when I was sketching you a proof of Alexandrov's theorem that convex functions are twice differentiable almost everywhere. Somehow, the idea of that proof also works in this situation. I don't know, maybe I should give this theorem a. So this was something, let's see. This is about a 10-year-old theorem. And I guess I proved it together with Brennan Pass and Micah Warren. So so I'm going to basically choose. So since dxyb at x naught y naught, you can think of this as a mapping from the tangent space. Oh, wait a second. You can think of it as a mapping in several different ways, and I don't care that much which way I'm thinking about it, but let me see. I could think about it as a mapping from I guess taking values in cotangent vectors, something like that. It's sort of a map from the tangent space at x naught to the cotangent space at y naught, or from the tangent space at y naught to the cotangent space at x naught, depending on which way you want to think of it. But since it's invertible, by using its we can rotate coordinates on y naught, or choose new coordinates. Let me not say rotate. We can choose new coordinates on m minus, actually using a linear change of variables. Invertible, which are basically given by the inverse matrix to this guy. Such that if I define b tilde of xy to be, I guess, b of probably x naught plus x, y naught plus this linear mapping, ay. So I sort of did two things at once. I moved x naught, y naught to the origin in the new coordinate system. But anyways, apart from moving it to the origin, which is not terribly important to the proof, but apart from moving to the origin, what do I want? I want such that this has the mixed partials with respect to the new variables given basically by the identity map. Does that make sense? right? The mixed partials of this thing are given by that. The mixed partials of this thing will be given by this times A. So I choose A to be the inverse of this, and I'm in good shape. And for it to have an inverse, I make this non-degeneracy assumption. And so what does that mean? That means at nearby points, since part of the assumption that part of the non-degeneracy assumption is that my cost is C2 in a neighborhood of X naught, Y naught. That means that near the origin, these mixed partials are given by, let's say, minus the identity. So for every epsilon positive, you can make this as close as you like to the identity if X and Y are small. And so that's let's say smaller than R. That's my neighborhood that I want. I give the neighborhood of new variables. I guess maybe you'd have to make it a little worse because of the change of variables. Maybe I'd have to take it X and Y smaller than R over magnitude A or magnitude A inverse or something like that. But anyhow, if I have a Lipschitz submanifold in the new variables, then I have a Lipschitz submanifold in the old variables, because that's one of the wonderful things about differential topology is that when you change variables, you may change the Lipschitz constant, but you don't change whether or not something is Lipschitz. Okay, great. So now so how do you say it? So there's okay, so now let gamma have be cyclically monotone support. Actually, so I really only cared about it being B monotone, but anyhow, so let's so recall gamma B optimal implies support of gamma is B cyclically monotone, which implies the support of gamma is B monotone, which means I don't really need this for arbitrary cycles. I only need it for cycles of length 2. And so if so let me suppose X naught, Y naught's in support of gamma, because all I need to do is show that it's Lipschitz near an arbitrary point in its support. Then XY in support gamma implies BXY plus BX naught Y naught minus BX Y naught minus BX naught Y has a sign, I guess, is bigger than 0. And another way to write this expression is it's kind of a double integral. Maybe I'll call this X1, Y1. It's sort of an integral from X naught to X1, integral from Y naught to Y1. And sorry, this should have been b tilde. I'm interested in doing this for b tilde. So it's the support of gamma and the new coordinates. So what I've written here is a little bit schematic. What I really mean is let's say, take the line segment joining x0 to x1 and the line segment joining y1 not to y0. And then if you integrate along those two line segments, this mixed partial, then you get something non-negative. Right, so this is really an integral from 0 to 1 ds, an integral from 0 to 1 dt of mixed partial. So this is dxi dyj, and then I would have x1 minus x0 I, y1 minus y0 j ds dt. But as long as x1, y1 are close enough, are within this radius of ball around the origin of radius r, then I know that the integrand here is the identity plus a small correction, epsilon. And so this would be, so let me call this guy delta x, and this guy delta y. So the identity term here is going to give me delta x dot delta y. And then the correction is going to give me something of order epsilon. So something, let's say, plus or minus epsilon times so when you say plus epsilon, where epsilon tilde is smaller than epsilon. And so, so if I neglected this term here, I'd be back in this situation where in these new variables, delta x minus delta y is positive, and we already saw in the proof of Alexandrov's theorem that if this is my x coordinate, this is my y coordinate, and I have new coordinates z and w, where z is like y plus x over root 2, and w is y minus x over root 2. We saw that non-negativity of this thing implies w is a one Lipschitz function of z. And so now I want to take into account what this error term does to that. And so if I set, set as we did before, if I set delta z to be delta y plus delta x over root 2, and delta w to be delta y minus delta x over root 2, then what I've just shown is that 0 is less than, well, what? So delta x, I guess, is delta z minus delta w over root 2, and delta y is probably plus. So what I have here is actually I'm not quite so happy with this the way I've written the error term here. what do I really mean? I really just mean that I can make, sorry, yes, I haven't written it correctly. It should be epsilon times, right, there we go. That's better. So here I have something like delta z squared minus delta w squared. And then I have this plus this error that depends on both. It depends on the product of delta z and delta w. But I guess it can all be controlled by delta z, delta w. Right, so if I it can be controlled, better yet, it can be controlled by delta z squared plus delta w squared. There we go. And so somehow, at worst, I have approximately delta w squared is less than delta z squared, and but to get this, I might have to subtract something, some part of delta w squared, and I might have to add some part of delta z squared. Great. And so this basically says that delta w is less than 1 plus epsilon tilde over 1 minus epsilon tilde delta z with a square root. And so I get Lipschitz again, but with up to this, the Lipschitz constant no longer 1, it's slightly worse than 1, depending on how big epsilon is. Any questions? Problems, difficulties? Okay, so that somehow tells us in the neighborhood at this point, I almost have there's a small neighborhood around this point where I have a submanifold where I can write W as a graph over Z. And Z here is in Rn and W is also in Rn. And so that's why I'm an n-dimensional subset of a 2 n-dimensional product space. This argument doesn't tell me anything about whether Y is a graph over X or not, but it does tell me that when I do this funny mixing of dependent and independent variables, that W is a graph over Z and Lipschitz, so differentiable almost everywhere by Rademacher's theorem. Okay, great. And so that's somehow nice because it works for rather general costs. All you need is this, and rather general measures. All you need is this non-degeneracy condition locally. And somehow that if you're in the context where twist holds globally, and so you have solutions to the Monge problem in the sense of maps between the source space and the target space, this, I think, makes it very plausible that those maps, when they exist, are going to be differentiable almost everywhere. Monge maps G for non-degenerate costs are differentiable almost everywhere when they exist. And you can also parlay this into a proof that if you assume the mu plus and mu minus are absolutely continuous with respect to Hausdorff n-dimensional measure and given by densities f plus and minus of x, it's plausible, I hope, that the derivative of the Jacobian of this map, which we now say probably exists almost everywhere, should be given by the ratio of f plus and x and f minus and g of x. Usually we bring this term up to the other side. And so that's somehow, in the special case of the bilinear surplus, that's the Monge-Ampere equation. And so you can sort of expect solutions to exist almost everywhere, at least for densities that are absolutely continuous. And in fact, this expectation is borne out. And I think you probably use tools from geometric measure theory, like the area and co-area formula, to prove this. Let's say for countably Lipschitz functions. So a function is countably, if you have a function that's not Lipschitz, but you can decompose it into countably many domains, and it has a Lipschitz constant on each domain, maybe getting larger and larger on the different domains. And in the same way that we had to be careful when we talked about Alexandrov's theorem about when I said, well, the second derivative exists almost everywhere, even though the first derivative may not exist on a dense set or something. So you have to be careful about in what sense do you mean the derivative here. And I guess the technical sense is the approximate derivative. So I should say approximately differentiable. But anyways. But it is a big jump from here to asking for these derivatives to exist in a classical sense, like everywhere. So somehow, right now, we know these approximate derivatives exist on a set of full measure, but it's far from being true that they exist everywhere, and that is that's somehow the topic of regularity theory. G to be differentiable or even continuous everywhere instead of almost everywhere requires much more. And you can sort of imagine this has to be true. So for example, if your source is connected and your target's disconnected, G is going to have a discontinuity in somewhere, because there's a continuous image of a connected set is always connected. And so you would need much stronger hypotheses that in particular require your support of mu minus not to be disconnected if you wanted to hope for continuity or differentiability of G. So I thought I would say a little bit about that. So for the surplus function B, for the bilinear surplus, there's a lot of work on regularity going back to, I mean, the main contributor is Caffarelli, but even there were some results before Caffarelli due to Delanoë, and it's in parallel with Caffarelli due to Urbas. And the situation is basically the following. Let's say 91 to 96 or so. Says something like, actually, you need more than just the target is connected. You need the target to be convex. So if and let's say the logarithmic derivatives of f plus and f minus are L infinity, are finite, So in particular, F minus has to fill M minus. So bounding the norm of log F says that F is bounded away from both 0 and infinity. Then G equals du is Hilder continuous. Let's say locally Holder in M plus, in the interior of M plus. I.e., there exists some exponent between 0 and 1 such that u is continuously differentiable and its derivative is Holder continuous. And then you can say more. This was basic, that was 91. And if both, oh yeah, wait, so there's more than this. If also log F plus and minus are smooth, and if you have only CK here, then you get the right number of derivatives on U. And so far, this is all in the interior of M. And then by 96, he had shown that if both, now I need both. If both M plus and M minus in Rn, probably bounded, they have to be bounded for the, okay, so I don't need to say bounded, are both convex. And I think he actually needed them to be two uniformly convex. So in other words, to have positive curvatures at every point on their boundary. And log F plus and minus the fact that F plus and minus are bounded away from 0 says that these sets can't have infinite volume. The set, and then being convex, they have to be compact as well. Then you become C1 alpha up to the boundary. So the map becomes Holder continuous up to the boundary. And if also, so let's say, I don't know, let's say this is theorem 1 and this is theorem 2. If also these guys are smooth up to the boundary. So the regularity theory at the boundary is a much more delicate issue than the regularity theory in the interior. And the regularity theory in the interior is already somewhat delicate. And let's see, there are actually two ways to go about getting results like these. So I should mention also, let me also mention Delanoë in 2 dimensions for the interior regularity for theorem 1, and Urbas in 96 in more dimensions, in all dimensions, but the boundary theory. So the methodology of Caffarelli was basically you start out with a weak solution, like a solution in the sense of Brenne. You show it's a little bit better than being a Brenne solution. So it's a solution what either the Alexandrov sense or the viscosity sense. And then you do kind of a blow up. You try to derive a contradiction. You say, well, if the convex function in question had 2 supporting hyperplanes, so it wasn't differentiable at some point, then let me blow up at that point. and try to do an analysis which says that I get a contradiction. And what he found was, of course, you can't get a contradiction based only at that point. You have to follow kind of the, there's these two derivatives and you sort of follow them, and the contradiction comes from following it to the boundary or something like that. So somehow regularity in these, because the equation is not uniformly elliptic when you linearize it like Poisson's equation, but it's only degenerate elliptic. So that, in other words, the coefficients are non-negative definite, but they may not be positive definite, because convexity only says that your Hessian is non-negative, not necessarily positive. You can't really get local, the equation is not locally regularizing. There has to be some compatibility between the equation and the boundary conditions in order to get smooth solutions. So somehow that was the flavor of Caffarelli's arguments. The Delanoë-Urbas arguments were quite different. They relied on something called the continuity method, which basically says you try to write down a one parameter family of problems, interpolating between some problem that you know the answer to, like, let me find the optimal map between mu plus and itself, which I know is the identity map, which is as smooth as can be, and the optimal map between mu plus and mu minus I'm interested in. And then let me interpolate between those two problems and try to study the first moment or the first interpolation parameter for which things go wrong. And so you know that the solution is smooth when the interpolation parameter is 0. You'd like to know it's smooth when the interpolation parameter is 1. And if you can show that the set where it's smooth, the set of interpolation parameters for which it's smooth is both open and closed and contains 0, then it must be the whole interval, and so contain 1 as well. And so openness comes basically by you have a solution where you know things are smooth, you linearize around it, and you use something like an implicit function theorem, a Banach-based implicit function theorem, to say that if things were good at that point, they're good in the neighborhood of that point as well. And closedness comes from what are called a priori estimates. So in other words, when you assume things are good, and then you try to show maybe that you have a second derivative or a fourth derivative bound when things are good that doesn't depend on how good they are. And so therefore, if you have a sequence of good solutions and you have these solution independent bounds, then you can pass the limit of that sequence and still have a bound. So that's how Delanoë and Urbas showed their results. So I certainly don't really want to try to say much more about their techniques. But what I am interested in talking about for a few lectures is how would results look for other cost functions other than the bilinear guy. And when Villani wrote his 2003 book, that was the big open question. He said, without a doubt, the big open question in the area is to show smoothness results for costs other than the bilinear fellow. And that it took about 5 more years after Villani's book for them to be some real progress on that question. And the first progress came through work of Ma, Schrödinger, and Wang. So I think, yeah, maybe it didn't take that long. I think their first paper was published in 2005. But of course, Villani's book existed in notes. He was circulating it in note form in 1998 already, or 299, something like that. Okay, and so Ma, Schrödinger, and Wang adapted these, began adapting these results to other B functions. But what they realized is that you need, what they realized was actually the bilinear surplus is kind of a delicate borderline case. So there's a class of B's for which it's possible to adapt these results. And this function lies on the boundary of that class. So there's also lots of B's for which these results don't adapt because there are counterexamples. And so let me describe some of the counterexamples. So I guess so regarding domain convexity, there was an example of Caffarelli. And this is still for the bilinear surplus. So if you try to map the disk to two disconnected disks, to two disconnected half disks, like this, right? So take the unit ball in R2 and take mu plus to be the uniform measure correctly normalized to make it a probability measure. And then the optimal map for that to itself would come as the gradient of the convex function u equals 1/2 x squared. But if you split the disk into two pieces and you push them some distance apart, I don't know, maybe 2r, then you would have to add something like r absolute x to this, and that would be the optimal map, absolute x1 rather. It's easy to see this is convex, and it's easy to see that this preserves the area. I'm putting uniform measure on these two half disks. And Caffarelli, he had a rigorous argument that you might say, well, the problem is that the target's not connected. And he said, well, disconnectedness is not enough, because if I modify this example by putting in a little bridge, which is enough to make it connected, like this, you'll still, of course, this won't be, you won't have an explicit solution anymore, but you're going to have a solution which converges to this one in a strong enough sense that it still has to, its gradient still has to have discontinuities. And then there's another series of examples which are due to which have to do with other costs. And these were proposed by Lopere, gosh, around 2008, I think. And I mean, actually, so this is my own take of counterexample. This isn't really Lopere's example, but it's my version of a counterexample. And so so Lopere said, let's contrast the situation when I do optimal transportation on Euclidean space to the situation when I do optimal transportation on the round sphere, and also to the situation where I do optimal transportation on the hyperbolic disk. So he said, let's consider three different costs. So I'm now switching from benefits to costs. So one of them would be, well, let's see, they're all going to be Riemannian distance squared on A, B, and C, and B is going to be Euclidean space, and A is going to be the round sphere, and C is going to be hyperbolic n space. Or you can take n to be 2 if you want. S2, R2, and H2. And of course, the case we understand best is this one. And what happens in that case, and let's take, so I'm going to take M plus to be one of these manifolds locally. All of these manifolds are R2 locally, at least topologically. But think about the case for a minute where M minus consists of just 3 points. So in other words, I have whichever model I'm in, I have some initial distribution mu plus, and I want to map it to a mu minus. These are still sitting in R2 or whatever. Mu minus is going to be a sum as I counts from 1 to 3 of a Dirac measure sitting at delta I, maybe with weight 1/3. So I have these 3 Dirac measures at y1, y2, and y3. And then I want to know which part of mu plus maps to y1, which part maps to y2, and which part maps to y3. And what does the theory tell us? So the duality theory says there exists, so I guess I have to call this minus b. It says there exists some b convex function. And if I think of the target as being just these 3 points, then what it means to be b convex is that u of x is a supremum as I counts from 1 to 3 of minus cxyi plus or minus a constant, which can depend on yi. And so, for example, so in the case of Rn or R2, the C here is quadratic, but it's much like the bilinear case. So in other words, if I absorb a term, if I add a term 1/2 x squared to u and I add a term 1/2 y squared to u tilde, then this is going to be supremum of a bilinear cost. And so I'll have basically 3 hyperplanes. And it's a bit hard to draw the picture, but if I were to look down on this, when hyperplanes always intersect, two-dimensional hyperplanes in R3 intersect in lines, and if I project that down onto the domain, I would have a picture like this, maybe. So everything over here will go to 0.1, everything over there will go to 0.3, and everything in here will go to 0.2. And it depends exactly where 0.2 is, right? So it could be, I could have this picture, or if I move 0.2 to this side instead, then this picture might change to something like that. And in the case 0.2 lies exactly on the segment joining, the line segment joining y1 to y3, then I could have, then the hyperplanes might be parallel, and I might have this. And these are, if you basically adjust these, if you adjust this constant a little bit, you can make region 2 bigger or region 2 smaller until it contains 1/3 of the mass, if I adjust the second constant. And similarly, if I adjust the first and third constant, I can make regions 1 and 3 smaller or bigger until they contain 1/3 of the mass. So that's more or less how you solve this problem in Euclidean space. By the way, this game of mapping a continuous measure to a discrete measure is sometimes called semi-discrete. And people used it to do numerics quite a lot. Semi-discrete OT. And that reminds me, I think, so a brand new book just arrived in my mailbox, authored by Gershon Wolanski, which is something like semi-discrete optimal transport. But I think that he actually means something different by semi-discrete, but I'm not sure. And he claims that he has a different route to optimal transport, which is accessible to undergraduates, and really starts heavily with the discrete case, and then derives the continuous case as a limit of the discrete case. Okay, so this was somehow the story in Euclidean space, except notice that in all 3 of these scenarios, all the regions are connected. And the Loper's point is that's not necessarily true in other geometries. And so now if I think about how would this picture change, I obviously drew this in the wrong place. So this is Rn. Now suppose that these 3 points, so suppose that my initial distribution lives on the sphere and these 3 points also live on the sphere. So I'm going to move to S2. But this part of the solution still adapts perfectly well to S2. And then the only question is, if I'm looking down on the Arctic Circle, so this was case B somehow. I'm going to go to case A, S2. I'm looking down on the Arctic Circle. I'm mapping all the mass in the Arctic Circle to these 3 points. What do the different regions look like? And so the answer is, looking down on the Arctic Circle, by moving the round distance squared up and down to these 3 different points up and down relative to each other, you tend to get pictures that look like the following. So there's some region around the North Pole that maps to Y2, and the region in the Western Hemisphere goes to Y1, and the Eastern Hemisphere goes to Y3. But all 3 regions are still connected. If I play the same game in hyperbolic space, using the hyperbolic distance, then when I look, so you can, if you think of a caricature, the caricature would be something like I have a saddle surface. And I have a big, I have I have a town that's located in the saddle, and it's farming, so wheat's being produced everywhere, and people are bringing their wheat to one of 3 depots to sell it. And then depending on the price at the different depots, they'll choose, and their location in the town, they'll choose which depot to go to sell their wheat. And then the question is, which parts of the town sell at which depot? And the answer is that if you look down on the saddle, what you will see is a picture like the following. So the east side of town goes to the first depot, the west side of town goes to the third depot, but the north and south corners of the town go to the middle depot. And so somehow something's topologically different because the set of people who are choosing to sell their wheat to the middle depot consists of two disconnected pieces. And somehow Lauper's insight was that once you have a picture like this, where you have these kind of disconnections, you can massage this sort of situation to produce a counterexample to continuity of the optimal map. And so let me try to describe how you do that. So what's the conclusion? One of the conclusions of Lauper and Matruni and Wang's work was that under suitable hypotheses for smooth densities on suitably convex subsets of the sphere, as well as Euclidean space, the optimal map between those densities will be smooth, but this is no longer true in hyperbolic space. So how am I going to massage this example? Well, so your first objection is this doesn't fit into the description of what I've been talking about at all, because although the source measure may be as smooth and bounded as I like, the target measure is very singular. It consists of these three Dirac masses. And I say, okay, that's not a problem. Let's mollify it. So let's define mu minus epsilon to be your favorite mollifier convolved with mu minus. So I've taken this very singular thing and I've made it into a smooth thing that has three big bumps focused very near the singularities. Right, so now mu minus epsilon at least is bounded away from 0 infinity and smooth on this target region. And I can choose the target region to be as convex as I like. And now I want to think, instead of thinking about the forward problem of mapping, the town in the saddle to these three depots, I want to think about the backward problem of mapping the three slightly delocalized depots, slightly smeared out depots, spreading that uniformly over the town. And the story is that when epsilon is very small, then what do I want to say? I want to say these borders get fuzzed a bit, but basically for epsilon very small, it has to converge to the picture that I had when epsilon was equal to 0. And so when epsilon's small, the stuff being produced in some neighborhood of at least all the stuff being produced well in the inside of region 1 has to go near point y1. And all the stuff being produced well in the inside of region 3 has to go near y3. And that doesn't leave enough. So except for this top and bottom region, there isn't enough. If epsilon's small enough, there won't be enough stuff in here to supply all of the demand at y2. And so that means that I need some of what's in this upper region up here, well, let's say in region 2, or let's say a slight neighborhood of region 2, and some of what's in this lower region down here, both to supply y2 under the forward map. And that means that under the backwards map, this region around y2 has to take some of its mass here and some of its mass here, but it has to be contained in this union of these two green dotted things, and so a discontinuity has to occur. So somehow that's the flavor of the argument. Is it clear, or was it too much hand waving? I have to say that, so I wrote this somewhere in a paper, I can't remember where, and the referees complained about it. They said it was too hand wave, that it wasn't rigorous enough, and they wanted us to make it rigorous, and we threw up our hands and refused. If you look in Lauper's paper, he actually he doesn't do this example. He has an example with just 2 points and some discontinuity. But for me, it's much less intuitive. So for me, this is a much more intuitive, I can sort of understand what's going on. And what's the intuition behind it? The intuition is I'm doing distance squared transport, which means it's like I'm transporting lettuces. I don't want to transport any individual lettuce too far because the cost for doing a long trip is growing like the square of the distance. And in this hyperbolic geometry, if you're at this corner of town, it's a long way to there or there. So you'd much rather go to the middle. And the same thing if you're on the opposite side of the saddle, you'd much rather go to the middle. But the guys in the middle, they're not so far from here and here. So they're willing to, so the guy in the middle, he's willing to go there, he's willing to go there. The price at this middle depot is not high enough for him to want to sell at the middle depot. It's only the people that are way out here on the outskirts of town that will choose to go to the middle depot where they're offering these low prices. And somehow that's the origin of the discontinuity. Okay, so I think it's about time to transition to office hours. If anyone wants to ask a question on the recording, I can take questions, and otherwise I will stop the recording.